All right, quite a few announcements today. Homework 1 search was due yesterday. There are no slip days on homework, so if you missed it, you missed it. The thing I want to highlight here though is that there's a button show answer that is available now. After the homework is due, the electronic part of the homework is a show answer button. If you click on that, you get to see the answer. Most likely you already had the right answer because you got the work till you got it right. But you see more than just the numerical answer. You also see an explanation of why something is the answer. So if you weren't sure, you solved something, but maybe you weren't sure why you got it right, go back, check the show answer button. It'll tell you why something is the answer. Project 1 search has been released last week, due on Friday at 5 p.m. Start early, ask questions, come to office hours. It's longer than most. I would say project 1 is the second longest project. Project 4 is going to be the longest one. You can do it alone, you can do it in a group of 2. For a group of 2, just a reminder, both of you need to submit. You'll submit the same code, that's fine because you're a group of 2 and you'll signal that you're in a group of 2. But make sure you both submit into edX or your grade will not register. Homework 2 on CSPS is about to be released. Will likely go out tonight if it's not out yet right now. Again, there will be a part 1 and a part 2. This will be the case for every homework. Due Monday at midnight. Exam conflicts. Today is your last chance to let us know about exam conflicts. We communicated on Piazza and edX on the syllabus when the midterms are going to be, when the final exam is going to be. If you have a conflict, email us at the staff list. Explain the nature of your conflict. We'll round them all up. We'll prioritize them in a certain way where we'll see what conflict is more severe than which other conflict. And then we'll just work down the list, see how many spots we have in the makeup, which is a limited number of spots, probably 10 or 15. The most severe conflicts will get accommodated for. The other ones you'll know by Friday you're not accommodated for. And you'll get to talk to your other professor in your other class to maybe get it resolved there or find some other solution. But deadline is tonight to be on that list of conflicts that we're going to be looking at and prioritizing among. If you don't reach us by tonight, you're not going to be considered at all in terms of conflict resolution. Sections. We had sections signed up to as much as 135 students signed up for one section. In terms of how many students showed up, none of the sections had 135 students show up. The most highly coveted time slot is this 2 to 3 p.m. slot on Thursday. 55 students. It's a little much, probably not as comfortable to be in a 55 student section. If you want to be in a quieter section, here's a roundup of how much attendance there was in each of these sections. Clearly we have enough slots. Every section can accommodate comfortably up to 30 to 35 students. Some of them have less or even significantly less than 35. The least attended one is Thursday, 6 to 7. Only 10 students, so clearly there is space for all students to find a seat. It's kind of up to you, I guess, if you want to be in a time slot you like better, but you're in a much more crowded section, then well, maybe a time slot you like less and be in a less crowded section. We'll report again next week so you again have an idea of how crowded things have been if you want to change section, where you might want to go to be in a quieter section. Any questions about logistics? All right. Happy Chinese New Year, everyone. It's the year of the horse. It's supposed to be a great year from what I understand. But there was also a little debacle with the announcement of the new year. Some of you might remember from first lecture, we had these closed captioning. We had the final goodbyes that kind of went wrong in the closed captioning we looked at in our first lecture. This was NBC. This weekend we had BBC transcribe things wrong. Here's what they came up with. Welcome to the year of the horse. All right. Speech recognition not totally perfect yet. No full understanding of context. All right. Second lecture on constraint satisfaction problems. Let's do a quick recap because we'll be building on what we saw in last lecture. We'll look at efficient solutions of CSPs and a new type of approach, local search. So what was a CSP? A CSP was something where you had a set of variables. Each variable had a domain associated with it. The set of values a variable can take on is the domain of that variable. And then there were constraints. Those are a set of prescriptions that our solution needs to satisfy, where a solution is a set of assignments, one assignment for each variable. These constraints could be implicit, where you say, for example, red and green is okay, blue and green is okay, green and blue is okay, and you list the compatible assignments of variables that participate in a constraint together. That's explicit. Implicit is where you provide a piece of code, something that says, for example, check whether the two values are the same or not. Often the piece of code is more succinct, but it might lead you to have to write more code yourself, whereas if you have explicit constraints, often you can feed it more directly in off-the-shelf solvers. Constraints could be unary. That means the constraint only involves one variable. That's equivalent to just saying I want to reduce the domain of that variable. They could be binary, involving two variables, or they could be n-ary, involving n variables in a constraint. Now, the goal in constraint satisfaction problems is to find a solution in what we've been looking at. Sometimes you might want to find all solutions. Sometimes you might want to find the best solution. Maybe there is no actual solution, but there's something that satisfies the most constraints and so forth. We're interested in 188 in finding any solution that satisfies all constraints. All the algorithms we've been looking at, that's what they're trying to do. Now, what we've been looking at in last lecture is how can we do something different here? This is still a search problem, but how can we do something different that takes advantage of the specific structure of this search problem to do something more efficient than a straight up, let's say, depth first search? And we saw that we can do backtracking search, and it looked like this. Just a couple minutes. Backtracking search looks like this. You have a recursive implementation here, but you could also implement this with a fringe in an equivalent way. You keep track of your current assignment. If it's complete, then you call it done. If it's not complete, then you select a variable that's not been assigned a value yet. For each value in the domain of that variable, you check if that value is consistent with the assignment that you already have. If it is, then you continue, you assign that value, and then you make a recursive call where now you have an additional value assigned, and that's how you will at some point end your recursion, because all variables will have been assigned. Then when you come back from this recursive call, you check if it returned a result. If the result is an actual result, so not a failure, you can return that result. If it returns failure, meaning somewhere along the way it realized it couldn't assign a value to the next variable anymore, then you backtrack, you loop around here, try the next value, and so forth. We looked at this. This is the basic backtracking search. We know there are two choice points. One choice point is over here. Which variable to select next? So we looked at variable ordering heuristics. Another choice point is to decide which value to look at first. We looked at value ordering heuristics. And another thing that we looked at is when we check here for what values are still possible, we might be shrinking domains as we go along. We might run filtering. As we make an assignment, we might run forward checking and prune domains of remaining variables and only retain values that are compatible with the assignment we've made so far. Or we might do something more advanced, such as enforcing our consistency, where we kind of cycle through the constraints until all of them are compatible with the assignment we have so far, and all filter domains have compatible assignments left. So those are the choice points we have here. Okay, so for variable ordering, we said minimum remaining values is ideal because that's looking at the variable first that has the least options available. That makes for the smallest branching factor in your search, which is a good thing. It also means that you make more informed choices because those variables you already have some idea of what is a good value to assign to. Now, for values, it was the other way around. When you choose between values, well, you know that you're going to look at all those values if there's going to be a failure. If you cannot find a solution anymore, it means all values will fail. Then it doesn't matter which ordering you use. If there's going to be a success in that current part of the tree that you're in your search right now, if there's going to be a success, and there's only success for one or not all of the values, you would want to first pick that value that leads to success, because then you'll find success sooner. So here you want to be optimistic, pick the value that's most likely to lead to success, because if none of them lead to success, it doesn't matter how you order things. Today what we're going to look at is structure. How we might be able to exploit the structure of the constraint satisfaction graph to find solutions more efficiently. Patrick, you had a question?
Yeah, just a quick question, because you said earlier that maybe instead of finding any solution, you might want to find the best solution. But that would require the problem to specify some sort of method for not just a solution is correct or not correct, but how to make a solution better or worse.
Yes, so in problems we won't look at in the context of this lecture, but other people might look at in the real world, you would specify goodness of a assignment of values to variables as, let's say, the number of constraints that have been violated. And the less constraints you violate, the better your assignment. But it's not a feasible solution until you have no constraints violated anymore. But so that would be one metric that people might use. Okay, the way we're going to exploit structure is actually to build an idea we've already seen, which is our consistency and beyond. So we'll look at it first. First, let's look back at our consistency. So remember, we have this mnemonic here that you always remove things from the tail. So let's say we're enforcing our consistency. We're running a search. WA and Q have been assigned red and green respectively. We have these domains here right now. If we were to run our consistency, what that would mean is we would queue up all constraints in our queue. Then we would pick the first one from the queue and check. Is this arc, for this arc, have we enforced our consistency? We need to look at the tail, which is here, and check if for every value in the tail, there's a compatible assignment in the head. Is there one for red? Yes, because blue is compatible. Is there one for green? Yes, because both of them are compatible. Is there a compatible assignment for blue? Yes, because red is compatible. So we don't prune anything when we enforce the consistency of this particular arc. Next one. Here, we just have one value in the tail, blue. Is there a consistent value in the head? Yes, red is consistent. And so we don't prune anything. You might say, well, I know blue needs to be removed from the head, but that's just not what we do. Enforcing consistency of this arc means to just look at the tail domain and delete from there whatever we can delete. Okay, as we then look at the arc in the opposite direction, we say, is there something compatible with red? Yes. Is there something compatible with blue? No. And so we need to get rid of blue here. We can keep going. Work through this. Now that blue has been removed, only red remains in the head here, and now we actually need to remove red from this domain here. So that's one thing that's important to keep in mind as you enforce our consistency. When you remove something from a particular domain, you need to reconsider all arcs pointing into that domain. All right, keep going. Our consistency helps us detect failure earlier than forward checking because we more thoroughly check whether constraints could still be satisfied in the future. If x loses a value, neighbors of x need to be rechecked. And you must rerun it after every assignment. Once you go down one level in the search tree, you make an assignment, you need to rerun our consistency. All right, we said, what could we end up with when you run our consistency? Well, you could have one solution left. This is a really nice case, because that means that all your constraints are satisfied. all your variables have one value left. So that means that that particular value for these variables is the right way to go and you have a solution. If you have multiple solutions left, well, you wouldn't necessarily know. Let's say you look at the scenario here or here. Both of them look like you have many values left. One of them has a solution, one of them doesn't. So if there are many values left in the domains, you just have to keep searching. You could be either in a multiple solution, single solution, or no solution regime. All can happen. So keep in mind you always run this inside a backtracking search to make sure that you can find out whether you have multiple solutions or no solution or a single solution left. All right, we can take this to another level. Our consistency, we can think of that as 2 consistency, k equals 2. Now let's see how we can augment this to higher numbers for k. So 1 consistency is node consistency, is enforcing consistency for a single variable for each variable. So you look at the constraints that only involve one variable, unary constraints, make sure they are satisfied. It's always very simple. It's just pruning each variable's domain to satisfy its unary constraint. Our consistency, or 2 consistency, looks at each pair of variables, looks at the constraints involving that pair of variables and makes sure that those variables, you look at one of the variables, check for each value remaining in its domain whether there is a consistent assignment for the other variable. That's 2 consistency. You can repeat this for higher numbers, any k. So k consistency, what that means is you pick any subset of k nodes. Now, that can be a lot of nodes if k is large. Then once you have such a subset of k nodes, you take any subset of k minus 1. So it'll be k of those subsets because there's k variables that you could leave out of k variables. So you take k minus 1 and you repeat that for every subset of k minus 1. Then for every consistent assignment of those k minus 1 variables, you check if there's a consistent assignment to the extra kth variable in that set. If there is, then that's good. If there isn't, then that combination of assignments to those k minus 1 variables is not valid and you throw it out. Note that you're here implicitly keeping track of joint assignments between variables, right? You'll have some kind of thing that keeps track of for these k minus 1 variables, this is the set of combined assignments that are still valid for which I can find something in the kth variable that is compatible. So you're having a much bigger representation underneath here to run this kind of consistency. So it's more expensive to do this. We'll only deal with k equals 2, but we want you to be aware of this higher order consistency and also be aware of what you can in principle do with it. So strong k consistency means that you are k consistent for k equals 1, 2, and so forth up to k. Here's a claim. If we have strong n consistency, where n is the number of variables in the CSP, then you can solve the problem without backtracking. Why is that true? Well, let's say we just enforced strong n consistency. Then we can now just pick any variable. For that variable, we pick some value in its domain, in its remaining domain, assign that. Then we choose a new variable. By 2 consistency, we know that for that new variable, we can assign a value that is consistent with the value we already assigned to the first variable. So that's fine. We can now go to 2 variables that are consistent. By 3 consistency, when we pick now any third variable, we know that in the domain of that third variable, there is something left. There is something there that is consistent with the assignment we already made to the first 2 variables. And we can keep going this way, and we get a full assignment. Question there?
Isn't this only valid if you have n or less nodes? Or sorry, n or less variables?
Absolutely. So n here refers to the number of variables. So this sounds great, but of course the catch is that enforcing strong n consistency is very expensive, right? Because you go up to n. At that point, you're looking at subsets of variables of size n minus 1, looking at all possible combined assignments of this n minus 1 variables, and seeing if there's a compatible assignment to the nth variable. So that's a lot of combinations to consider to enforce n consistency. But in principle, it's the way you could go. And you can imagine you could, on the spectrum of doing no filtering to then doing forward checking, which just checks with your current assignment whether the values in the domains are still compatible, to enforcing R consistency, which is 2 consistency, then maybe you might go to 3 consistency and say that's still reasonable to do as a filtering step and might help you with your search. And that depending on the problem you're looking at, there might be a sweet spot there around between forward checking, 2 consistency, 3 consistency, maybe 4 consistency, but very unlikely it would be N consistency. Question here.
If you check the inconsistency, isn't that just solving the problem anyways?
You are, yeah, if you check inconsistency, you solve the problem. You did all the work, and you can then read off an assignment with this procedure here. You probably did more work than any backtracking search would have done.
Yeah, that's what I was asking. Would it be equal, or you actually end up doing more work than using a backtracking search?
Potentially there are clever ways to check this that are equivalent to running a backtracking search, because in some sense it's doing the same thing. But if you just do it in the naive way, definitely, I imagine you'll do more work than the backtracking searches we've looked at. Okay, so that's one way to solve CSPs in a somewhat different way than we've looked at. Let's now look at something quite different, a whole new idea. And this idea will come back in the second third of the course quite intensely, in that we'll look at it in the context of Bayes nets, probabilistic models over large sets of random variables. Right now we have deterministic models over a large set of variables. Determinism is in that the constraints are deterministic. We know how they need to relate to each other. All right, so let's look again at a constraint satisfaction graph, as we see over here. Remember that we said, well, the fact that this graph splits into 2 separate graphs means that really we can solve 2 separate problems here. And so even if we have, initially a larger problem, we now have 2 smaller problems, that might be beneficial. Let's do a little calculation here. Let's say you have n equal 80 variables, binary domains, so d equals 2. And you have clusters of size 20. So you have, in this case, you have 4 subgraphs. It falls apart into 4 subgraphs, each of size 20. If you do the naive backtracking search, and you kind of look at the size of the search tree that explores, well, binary domains, 80 variables, so you have 2 to the 80 possible combined assignments to consider. If you can explore 10 million nodes per second, which might be reasonable, this will take 4 billion years to explore all possibilities here. Not saying our backtracking search with forward checking and so forth would explore all possibilities, but just to get an idea of how large that search tree is that we're dealing with, it's this large. If you realize that this is 4 separate problems, then you end up solving 4 times a problem of the size 2 to the 20. This would take 0.4 seconds at the same speed of exploring 10 million nodes per second. So the way we split this up, this exponential growth is so bad, having such a split really can reduce how much computation we need to do. Do you have a question?
Yeah, so just quick curiosity, what does D represent here?
D is the domain size. So in this example, domain size was 2, so binary values for the variables, but it can in principle be any domain size.
Okay.
Yes?
And when they say the clustering, like if I use the graph up here, it'd be like taking pizza slices, right? So like 3s.
No, this graph would only fall apart into 2 pieces so far. So that's the bad news. The good news is that if your graph falls apart into pieces, this is awesome because now you get to exploit this. The bad news is that almost no problems will fall apart into pieces because then really they are separate problems. Why in the first place did you present it as one problem? It was really separate problems. So that's the bad news. But we're going to resolve some of that bad news in the next couple of slides, in not making it as bad as it sounds. All right, so what we're going to do is we're going to look at a different kind of graph structure where we can also exploit structure to have a more efficient approach that's not as strong an assumption as falling into pieces. So we're going to look at tree-structured constraint satisfaction problems. So if the constraint graph has no loops, which means it's a tree-structured CSP, the CSP can be solved in order n d squared time, where n is the number of variables, d is the domain size. Compare that to general CSPs, where the worst case running time is order d to the n, exponential in the number of variables, versus linear in the number of variables. The nice thing is that now we do have problems where all the variables are in some way related to each other through this graph structure. You don't need separate problems. You can have one big problem. As long as it's tree structured, we apparently have an efficient solution already. Okay, let's take a look at how this algorithm works. So here's how it starts out. You have a tree structured CSP. You choose a root variable. What do I mean with choosing a root variable? You can pick any variable as your root variable. It doesn't matter. So you can run this algorithm many different ways for any given tree structured CSP. Because your first choice point is just pick any variable as your root variable. Once you pick your root variable, you hold up your CSP graph by that root variable. It's as if you grab it by its ankle, shake it out, and let everything hang down. Once you do that, what you get is a linearization of your graph. So here's an example of a linearization. There are many linearizations of this graph. Even with choosing A as the root of this linearization, we still have more than one linearization. There's no reason E has to come before F. There's no reason C has to come before D, E, or F. It's just one linearization out of many. Okay, now I have a linearization. Let's take a look at how we can solve this CSP. Let's assume these are the domains that we have for these variables. What we're going to do now is a sweep through this linearized CSP graph. And we will move through this graph, in this case, so we're going to do our consistency. We're going to be removing things from the tail again, right? So we're consistently removing things from the tail, and we're working through this graph right to left. So we'll start on the right, and we'll apply this arc consistency to arcs that we see in this graph. Only the arcs that are visible here. Note that in principle there's an arc running in the opposite direction for each one of those. We don't have to consider those. We just consider the ones that are shown here, consistent with the linearization we picked. So we start all the way on the right, and we check this first arc over here, F and D. What do we need to do? We need to check the domain of D and make sure there is only values left in the domain of D that are consistent with what we have for F. So what happens is we end up getting rid of blue, because blue has nothing consistent in the domain of F. We move on to the next one. So now we're at E, D to E. What do we have here? We have green in E. There is red that's compatible in D. Hold on. We need to check the domain of D. There is red. There is something compatible in E. That's good. There is green. There is something compatible in E, namely blue. So that's good. Next arc is the one from B to D. We check the domain of B, and we have green, which doesn't have a compatible value in, hold on, let's do them one at a time. Let's go with B. Let's highlight this in color. Let's start with B, still white. Let's go with B to D next. So we look at B to D. Is there something in D that's compatible with green? Yes. Red makes that work. Is there something compatible in D that's good for blue? Yes. Both of them make it work, so nothing gets pruned there. Then we look at B to C. Is there something compatible for green in C? No, because we only have green in C, so this green disappears here. Something compatible for blue? Yes. Then we're at our last arc here, A to B. Red, is that okay? Yes, because blue is compatible. Blue, is that okay? No, because there's only blue left. So at this point, we're left with the following set of filter domains. That's our first pass, right to left. Remember in regular enforcing arc consistency, we would cycle through the arcs and so forth. We're not doing that here, just one pass right to left. Then we have a forward pass. In the forward pass, what we do is we pick values left to right. So we start at A, we only have one value left, red, so we just pick red. Then we go to the next one, B. We have only blue left. So we pick blue. Are we guaranteed that's okay? Well, we have a constraint here between A and B. We enforced our consistency for that. We enforced consistency for that particular constraint here. What does that mean? It meant that any remaining value in the domain of A had some compatible assignment in B. So that means whatever we picked for A, now we land at B, there will be a compatible assignment. And indeed there is. Blue is compatible with what we had for A. Moving on to C. Again, we enforced consistency of this arc over here, which means that for anything left in the domain of B, there was something compatible for C. So no matter what we picked out of this domain of B, we happen to pick blue, we know there's going to be something compatible for C. And indeed, there is something compatible, green is compatible. We move on to D. We enforce consistency of this arc over here, B to D. And as we go along, you see there's always only one arc coming in, right? So the one arc coming into D, we enforce consistency, which means that no matter what we picked for B, there will be something compatible in the domain of D. And in fact, both of them are compatible. So we can pick either one of them. Let's pick green. We continue, we're on to E. We enforce consistency of the arc coming into E. We know what that means. It means that no matter what we picked in D, for D, there will be something compatible in the domain of E that's left. And indeed there is. Blue is compatible. Moving on to the last one, F. We enforce consistency of the arc that comes into F. We know that no matter what we picked for D, there will be something compatible in the domain of F with what we picked for D. And indeed, blue is compatible. And so what we saw happen here is in this pass left to right, we were always able to pick something that was compatible with the constraints that we could look at so far based on all variables that have been assigned. And by the time we finish, all constraints have been considered and have been satisfied. And we have found an assignment. So this is order ND squared. Why? Well, enforcing consistency of an arc is order D squared. And the number of arcs we need to consider is order N, because every variable can have at most one arc coming in the way we linearize the graph. That's how things come out. If you have a tree-structured graph, you cannot have more than order N arcs or edges. And the passes consider every variable, so that's also order N to do a pass to reassign. Question?
It says assign forward for I from 1 to N, but the thing is that when N is 1, or rather when I is 1, there is no assignment for parent of I. So shouldn't it be from 2 to N and then just take an arbitrary assignment for the first?
Yeah, so this is typically when we put things on the slides, we try to avoid getting long pseudocode to have all the corner cases for the first index and the last index and so forth. So you're absolutely right that for the very first assignment, there will be no parent. And so one way to read this is as assign x1 consistently with the parent of x1, which is an empty set of parents, and so nothing has to be considered there. All right, so tree-structured CSPs allow us to first pick a root, which could be any variable, hang everything up by that root, take a linearization according to that, do a right to left pass to prune domains, do a left to right pass to assign, and we found the solution. Okay, how do we prove that this always works? The first claim is that after the backward pass, all root to leaf arcs are consistent. Why is that true? When we did this backward pass, we would look at first this arc over here. We would make it consistent. The only way we could make this arc inconsistent after we made it consistent is by pruning something from the domain of the head variable. Because that's the way you invalidate consistency of an arc, if you move something from a head variable of that arc. But since we move right to left, Once we make an arc consistent, once that's happened, we never prune anymore from that head variable. It's not going to happen. And so once it's made consistent, it remains consistent. We never lose it. All right. So that's our first claim. That holds true. Second claim is, if indeed the route to leave arcs are all consistent, then a forward assignment going from left to right will just work out. You will not have to backtrack. You can just keep assigning as you go along. As long as the new assignment you make, from the values you have available, you pick something that's consistent with the variable where your arc is coming from, right? For example, when we picked an assignment for B, that assignment was chosen to be compatible with whatever we already picked at A. This can be shown by induction, and I'll just show the kind of by example proof here. Let's say we were to assign something to B. We know that whatever was left for the parent of B, everything in there has a compatible assignment in the remaining domain of B, so we can find something for B that is consistent, and this just keeps going on left to right. Okay, this sounds really good. So where does it break? Why does this work so beautifully for trees and not for graphs with cycles? Graphs with cycles, there's some kind of looping effect. Imagine that you have two edges coming in. Let's say we had an edge from D to F and an edge from E to F. If we were to do our right to left pass, which we certainly can do, what we end up with is a domain for D such that whatever we pick from D, there is something compatible in F. Whatever we pick from E, there is something compatible in F. There is no guarantee that whatever you pick in F to be compatible with D is the same thing that you would pick in F to be compatible with E. And so you might end up with maybe picking green to be compatible with D, but red to be compatible with E, and now you actually don't have something that works out. And so key here is that every one of these variables has only one arc coming in. And that only happens if you have a tree-structured CSP, and you linearize it and work through it this way. Patrick. Okay, maybe we'll come back to it later. Question?
So would there be a different algorithm if instead of linearizing it, we did a DAG?
So if we had a DAG, a directed acyclic graph, right, which is not necessarily a tree, it just means that if you follow the arrows in your graph, you cannot make a cycle, but if you ignore the direction of the arrows, you could make a cycle, right? Then it's not guaranteed to work, because this here is an example of a DAG, and we just discussed why you're not guaranteed to get something that works out here, because now you have two parents for a single node, and then the whole reasoning doesn't work out anymore. Question here. So the question here is, how does this relate to K consistency? I think that'll become a little clearer later. We'll have something that is closer to K consistency that also relates to structure in a couple of slides. All right, so the good news is that we can solve tree-structured CSPs very efficiently. Sometimes that's a good thing. Sometimes you can maybe design your problem to retain tree structure. You say, well, I know I can solve those efficiently. Let me only allow for tree-structured CSPs because I know I can solve them efficiently. But sometimes your CSP just doesn't have that structure. In fact, most of the time, if you write down the most natural way, whatever problem you're solving, you really write down what you want to be solved. Likely it's not a tree. All right, so an idea we'll see here, and I'll come back with base nets, is that these tree structure things are easy to solve. A lot of things are not trees, but we can make things into trees. So we can get rid of some nodes in the graph and make something into a tree. That's the idea we're going to look at right now. So let's say you have a nearly tree-structured CSP, this one here. This one is nearly tree-structured. The culprit is this node over here. If that node were just to be removed, you have a tree-structured CSP. Okay, so here's what we're going to do. Something called Cutset Conditioning. That is, you pick a set of variables. If you remove that set of variables from your graph, you end up with a tree. Okay? Then that set of variables, removing it, of course, changes the problem. We cannot just remove that set of variables. What we're going to do is we're going to cycle over all combined assignments to that set of variables. Once you make a full assignment to a set of variables, enforcing the consistency with those variables can be done through unary constraints, right? Because if you remove this variable, and once it has a particular assignment, enforcing this constraint is now just a unary constraint on this variable over here. And so we can kind of push the constraints that relate to the variables that we remove into the variables that remain. And we have our tree-structured CSP that remains. We just have to cycle over all possible assignments of these remaining variables. What does it take to cycle over those variables? Well, domain size D, we have a cut set of size C. So D to the C, possible combinations to consider. Then the remainder graph has size n minus C, and then D squared. So this is the running time of solving a tree-structured CSP. For that, a particular assignment of the other variables, we solve the tree-structured CSP. If there's a solution, we're done. If there's no solution, which by the way would manifest itself in the right to left pass, in that you would end up with a domain that's empty somewhere, right? If you have an empty domain, you know there's no solution, then you would pick a different assignment to the C variables that you pulled out and try again. So you again have a search algorithm here. You would choose a cut set. For that cut set, you instantiate different values. In this case, the cut set has only one variable, but there could be more than one variable in the cut set, in which case you get a backtracking-like search. You get branching, multiple layers. Then once you have cut out enough variables that there's just a tree structure left, you solve the tree-structured CSP. If you found a solution, you pass it back up. If there's no solution, then you know you're backtracking your search. Question over there.
Is there any official way to test whether you do have a tree-structured CSP?
Is there an efficient way to check that? There are algorithms that can check whether your graph has cycles. We don't look at these here, and I can't recite one out of the top of my head, but there are efficient algorithms that can check for that. Yes?
Is there any reason why you have to enumerate all three different? Can't you just choose one since the domain is going to be the same throughout?
Okay, so the question is, do we need to enumerate all three of them here? In general, this is what your search tree would look like. And you would first go down this path here. If you find something, you would never consider this part of your search tree. But if you didn't find anything, you then would go down this path. For this particular problem, because it's graph coloring and it is set up in a way that, honestly, if there's no solution with blue, there's not going to be a solution with red either and not a solution with green either, because there's some permutation of colors that you can do on everything and it's still a solution, right? So for this particular case, indeed, you could do additional, put in a little bit of additional knowledge saying, for the first region I color, I only need to consider one color because it doesn't matter what that first color is. But in general, this is what your search tree would look like. Question?
Yeah, so one way of checking if there are any nodes which can be cut out, could it be like you check if one node is connected to many nodes and then from that one out, cut that one out?
Absolutely. So one way to do this, to find a cut set, is a greedy strategy where you check which node has the most connections, right? Not just the most connections, but connections that result in cycles and cut those out. There's several algorithms out there that help you find small cut sets. For the purposes of this class, we'll only ask you to kind of generate cut sets for us where you can eyeball the cut set. So we'll actually do that right now. Here's a little quiz. Give you 30 seconds to chat with your neighbor and decide on what the smallest cut set is for this graph over here. right, any suggestions for a smallest cut set? Who has a cut set of size 1? No one has one of size 1. Who has one of size 2? All right, let's pick somebody from the back, over there. A and B is a suggestion. We cut out A and B. We're left with essentially this chain over here. A chain is a special type of tree, and we're done. So that's a smallest cut set. In fact, I think it's the only one of size 2 that we can pick here for this particular graph. In general, the heuristic is to look for very highly connected nodes, but of course they don't have to be the very highly connected nodes. If you had an additional set of variables sitting here, just in a star shape, it doesn't mean you need to cut out C, because there's no cycle sitting over there. Once you, of course, have more edges here, cutting out C could be the right thing to do. All right. That's one way to do a tree decomposition. It's you take a cut set and make the graph into a tree. Turns out there's another way to make things into tree structured problems. And the idea here is to look at your graph and actually structure it into a tree directly. And somebody made the suggestion earlier. Can you make this into a tree by looking at this as one component, then maybe this as the next component, then maybe this as the next component, and then this one over here. Right? If you look at the graph that way, you get a sequence of 4 supernodes in this case, and that sequence is a tree. Now each node in that tree is a supernode, has many variables in it. So it's a more complicated CSP in some sense because the variables are having larger domains, but it does make it into a tree. So here's what that looks like. Right? We'd have these 4 supernodes. Each of these individual supernodes are smaller CSP problems in and of themselves. Here we have 3 variables, constraints between them. That's a CSP. But it doesn't fall apart in those 4 pieces. If we just let it fall apart, the solution we find here might be not compatible with the solution we find here. And NT appears in both cases, and SA appears in both cases. So what we need to do is need to put constraints between them. So we make these supernodes, we put constraints between them, and the constraint between the supernodes is that they have to agree on the shared variables. Turns out you can do this with every graph. You can always make it into this, what is often called a junction tree. And that junction tree has these supernodes in which there is many of the original variables, and you can make it into a tree-structured graph. The one thing you have to pay attention to as you do this is that you need to make sure that wherever a variable appears, let's say Q appears over here, right? So 2 things you have to pay attention to. First one is all your constraints have to be present somewhere. So whatever edge you had in your original graph needs to appear inside one of these supernodes, which is the case in what we did here. Every edge, so every constraint is inside one of the supernodes. Then to make sure they all agree on the assignments to the variables, we said agreement is sitting on these edges here, but you need to be careful. It's not just that you need to agree on these edges, right? You need to agree everywhere where a variable appears. Otherwise, you might still have incompatibilities. And so as you construct this new tree, you need to make sure that if a variable appears somewhere, let's say a variable SA appears here and it appears here, then along the path between those 2 appearances, it has to appear everywhere. If you're sure that's true, then making sure there's agreement between variable on each of the edges makes sure that variables always agree on their assignments, because wherever you have variables appear multiple times, there's a sequence of edges connecting them, and on the edges, compatibility is enforced. So 2 conditions. One of them, your constraints have to be inside a supernode. Second condition, the variables, wherever they appear, you need to make sure that there is a path between their appearances where in every supernode along that path, that variable also appears. If that's true, and you have a tree structure, then you have a tree decomposition of your original problem, and now you can solve it efficiently. How efficiently depends on, remember, running time, order, and d squared. So it depends on the size of the domains. The domains are growing here, right? No free luncher. It's not that you can all of a sudden solve general CSPs very efficiently. If you have what is intrinsically a difficult CSP to solve, you'll find out as you try to construct these trees that you can never find such a tree unless one of the nodes in your tree is just really large and this super variable in that node has a very large domain. And that's where you'll pay the price. Your D will have become larger because it's now a different domain. It's the domain of one of these super nodes could be very large. This star over here, whenever that appears on a slide, it means this is an idea that we think is really important for you to be aware of, but at the same time it's an idea that we're not going to quiz you on. So that's something to keep in mind. So if you're really stuck on this and you're really excited about this, come talk to us about in office hours. But if you're just stressed about it because you don't understand it, but you just care about your points, not about understanding it, no reason to stress out about this particular thing. All right, let's take a short break here and look at a different class of algorithms after the break. Let's move to a completely different approach to solving CSPs. So far we've seen a bunch of ideas. We've seen backtracking search. Then we've looked at what if your CSP falls apart into pieces, exploit that structure. We've looked at what if it's a tree-structured CSP, you can exploit that. What if it's almost tree-structured? You can do Cutset conditioning and then exploit the tree structure. Or you could just force it to be tree-structured by introducing super variables and have a tree structure in your super variables. Right now I'm going to look at something completely different, iterative improvement. So how does this work? This is a first example of a local search method. A local search method is not going to be complete. It's not going to be something that's guaranteed to find a solution the way other methods have done that for us. So how do they work? Typically you start with a complete assignment, but that assignment doesn't have to be perfect. So for example, you could start with red and red for this 2-node graph coloring problem. It's not correct, but that's a starting point. Then what you need to apply this iterative improvement algorithm is you need to have something that can find constraints that are not satisfied yet. Or more specifically, you need to find variables that have constraint violations. Then you pick one of those variables, you reassign a new value potentially to that variable, maybe the same value, but you assign something to that variable, and now you have a new complete assignment. And you keep iterating this, where you update one variable at a time in the hopes of at some point reaching a solution. This is very different. You don't keep around the fringe. At any given time, there is one complete instantiation of your variables. That's all you have. There's no notion of a search tree where you keep track of what you've looked at before. As you can imagine, that this kind of search doesn't allow you to come back and say there is no solution, because you don't keep track of what you looked at before. You just have something right now, you change it, and you hope it gets better and better over time. So that's an update you might do. In this case, it's successful. What does the algorithm do? Select a variable. In our case, that would be randomly select any conflicted variable. Why randomly? Well, these things are very local, and if you introduce some randomness, they tend to work better. Value selection. The min conflicts heuristic will then choose a value for that variable that violates the fewest constraints. The result of that is that after your new assignment, you should end up with at most as many constraints violated than before, and likely less constraints violated. And that's the hill climbing aspect here. As you go along, less and less constraints are violated as you make a new assignment. And you hope that at some point you hit the 0 constraints violated and you're done. All right, let's look at an example here. 4 queens. Let's say you start with this assignment over here. There are some constraint violations there, right? We could pick a variable. In this case, we have every queen has its own column. We picked this one over here, the second column, and said let's reassign that to an assignment that has the least constraint violations. The one in the top row is a good one because it has 0 constraint violations, so that's the one here to pick. We end up with this configuration over here. Again, we look at any of the variables that violate constraints. There's 3 of them in this case. We randomly pick one of those 3. In this case, we picked this one over here. It doesn't have to be the one that violates the most constraints. It's any one of them that violates constraints. we pick this one. Once we pick one, we assign the value that's best, that violates the least constraints. In this case, this option over here is best, and we're done. So in 2 steps, starting from something random, we made 2 steps, we found the solution. Okay, that's pretty fast. Let's look at how this can play out kind of in a 5 queens problem. So what we have here is a row per queen, so every queen corresponds to a variable that needs to assign some column value. In this case, all 5 variables have constraint violations, so we pick any one of them. Let's say we pick this one over here. Now it displays how many constraints it violates. Okay? Well, we know that we picked the new position, the new value that violates the least constraints, so that's over here. Now again, we pick any of the variables that violates constraints. Let's say this one over here. Now we pick a value that violates the least constraints. We have a 3-way tie here. Let's pick maybe this one over here. Now again, we pick a variable that violates constraints. Could be any one of them, and we might go back to a variable we already had. We might go back to this one here. Say, well, that's our random pick. We look at whatever assignment violates the least constraints, 3-way tie. Maybe we now put it over here. Now again, we pick a variable that violates the least constraints. We pick a variable that violates constraints. There's 4 of them. We pick any one of them. Let's pick this one here. Then place it where it violates the least constraints, which is over here. Now only these 2 violate constraints. Randomly pick one of those 2. Let's pick this one here. Maybe we just keep it in place, because that's one of the 2 options where it violates the least constraints. Now we randomly pick a variable again. Maybe this time we pick this one. Place it somewhere it violates the least constraints. Maybe we place it over here. Again, pick a variable that violates constraints, 2 to pick from. Let's pick this one here. Now we can move it to 0, and we're actually done. One thing I want to emphasize here is that as you do this, the same variable can reoccur more than once. So it's not like a backtracking search where each variable has some kind of layer and you keep going until you hit the bottom. You just kind of cycle through variables somewhat at random. As long as a variable violates a constraint, it's in consideration to be randomly picked. Yes?
Wouldn't it be more effective to pick the variables that violate more constraints?
There is some intuition there that if you violate more constraints, probably it's more important to update that variable. The downside of that is that you're more likely to get stuck in a position where you keep picking the same variable. That variable violates the most constraints, and there is no way to improve the number of constraint violations for that variable, and now you keep picking that variable, and it's just getting the same assignment. So you need some more bookkeeping then to make sure that you wouldn't keep going back to the same variables and so forth. The randomness makes it a simpler algorithm to implement and works pretty well. Yes?
So if you're already picking them randomly, can you just update your probability distribution to make it so you pick nodes that are violating more constraints more often?
That's a great suggestion. So the suggestion is, why not have a distribution? So you at least favor the ones that violate more constraints. And I'm going to guess that there is something out there, some paper describing that you might get some benefit from doing that. Yes?
So this is actually a very human method of doing it in terms of, it's almost you can think of as trial and error. So we're not actually really coming up with an entirely new solution structure. We're simply doing how a human would solve a problem, but very much accelerated.
I'm going to argue that depends on the human, but I'm also going to agree that for a lot of humans, indeed, they would probably start with a hunch at what might be a solution and try to fix it up. Absolutely. And this is what this is trying to do. Fixing up something that's almost right and hoping that you get there. Let's look at another example. So let's go back to this problem here. Remember from last lecture, we looked at various backtracking searches through this coloring problem. What you see now is a random initialization. Edges that are colored in yellow are signaling constraint violation. All right, so we have a random initialization, and let's see how long it takes running this iterative improvement to get to a solution. So next ones, one variable got updated, and we see some constraints got unviolated, some might have gotten violated now. Second update, third update, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12, 13. So 13 updates is all it took, which is even less than the number of variables in this problem, to get to a solution. Generally, you can imagine if there's a lot of solutions out there, a very dense space of solutions, this is likely to find a solution for you reasonably quickly, but if there's very few solutions out there, well, it's going to have a hard time to finally zone in on that one solution. Okay, so how well can you do in the n-greens problem? We saw that you can maybe go up to 1,000 or 10,000 with a really good backtracking search. With this min conflicts procedure, 10 million, no problem. So find solutions very quickly. Let's look at a little more detail at what's going on here, right? If you look at CSPs, constraint satisfaction problems, and you think of them as a class of problems, people have studied sometimes what are the hard ones. You could say if this min conflicts procedure finds a solution very quickly, I could call that an easy problem because I know that if I draw a problem from that problem class, usually very quickly I found something. So people run these experiments and look at the kind of average CPU time as a function of the type of problem that you're trying to solve. And what they found that there's this thing, this horizontal axis here, R, the ratio of the number of constraints to the number of variables that determines how hard your problem is. There is this sweet spot, which is the bad spot, by the way, where the CPU time is really, really large. If you have that particular ratio, around that ratio, your problems are hard. What's the intuition here? Well, if your number of constraints is really large compared to your number of variables, if you run a backtracking search, you'll very quickly realize that you can backtrack. So many right away a constraint will be violated, you backtrack. And you don't have a whole lot of search tree to explore to realize that there's no solution. If there are very few constraints compared to the number of variables, and as you go down your search tree, you're likely to be lucky. You'll just find a solution, or if you run min conflicts, a couple of fixes, and there you are. You found a solution. The difficult spot is this one here, where there's just a few solutions out there. Right? Number of constraints, relative number of variables is such that there's just a few solutions out there, and you really need to do work to go find that one of those few solutions that exist. Okay, what does this look like in real life? You have the space of problems. The hard problems are this small little patch that is kind of embedded in this huge space of problems that are easy to solve. That's the good news. The bad news, which you know is coming, is that your problems will usually be there. And that the problems where you are actually interested in solving them have this property that they're hard problems and you somehow still want to find the solution. Okay, let's summarize CSPs and then let's take a look at how we can generalize this local search to other problems than just CSPs. So what was a CSP? States in our search problem correspond to partial assignments. The goal test is defined by constraints all having to be satisfied. The basic solution is a backtracking search. You can augment the efficiency or make it more efficient by using ordering of variables and values. You can use filtering to find early failure cases and to help you with variable and value ordering. And then there is structure that you might be able to use to, let's say, make it into a tree structure problem which you can solve more efficiently. Then there's this whole other class of problems, solution methods, iterative min conflicts, where you just reassign values. You don't keep track of what you looked at before, but it can be quite efficient. This is a special instance of something called local search that can solve actually quite a wide range of problems. So let's take a look at what local search looks like in general. Okay, let's first contrast it with tree search. Tree search is a search where you keep track of everything you looked at so far so you can exclude things that you very kind of in a structured way explore all possibilities till you find what you were looking for. Local search, you just keep track of your current best thing and just keep tweaking it and you hope that you find a solution. Much more memory efficient. You only keep one instantiation of all variables in memory. It can be very efficient, we saw. The main downside is lack of completeness, right? Because you're now not guaranteed to find a solution. You could go down some wrong path and keep updating things that don't get you in the right spot. So let's take a look at what this looks like picture-wise, right? It doesn't need to be complete, because what are you doing? You repeat this process over here, something called hill climbing. You're saying, I have a current point that I'm at, which is an assignment to the set of variables, and let's take a look at what can I do to improve things. But what does that mean? You have this big search problem you're trying to solve, and really want to get to the goal temple over here. That's where you want to be. But all you see in this hill climbing formulation is where you are right now. You say, what if I change this one variable? What if I change this one variable? What would it do for me? Think of it as trying to get to the top of a mountain, but there's so much fog, all you can do is kind of feel in all directions and see which direction is kind of taking you uphill. And then you take a step in that direction. And then you again feel around yourself, what's the uphill direction? Take a step, keep going. This particular case, where would you land? You would land right here. And that's it. You would not find this top. All right, so it's not complete in the sense it's not guaranteed to find the right solution if there's something like a right solution, a best solution. It's not, it can get stuck. It can get stuck, keep computing forever. Sorry, let me rephrase that. It's not complete because it can keep computing forever and not find anything. It's not optimal because it can find something like this, whereas something like this also exists. So what's good about it, it's very fast, and often in practice it can work well. Here are the failure cases. So you could start over here, you would go up here, you would find this point over here. That's called a local maximum. Locally, that's the best you can do, but it's not a global maximum, because the global maximum is over here, it's even better. But locally, if all you can do is move left, right, there's no room for improvement. So local maximum. Some of these local maxima can be flat. So there's a whole region where you're locally optimal. But it could also be the case that you're in this kind of flat region, but it's not a local optimum. Actually, when you hit this spot over here, you should keep going until you finally find some slope again, and you can keep climbing up again. You can't distinguish those. Locally, if it's flat, you don't know if you were to keep going that maybe you would hit an upslope again, or maybe not. So sometimes it's a very naive algorithm. It's just locally looking to improve. But the beauty is that in practice it can work really well. And often you augment it with some randomness, right? You might say, I'm going to start from 1,000,000 random initial points. Each one of them I run a local search, find locally what's the best, and maybe one of them had a good starting point and ended up climbing all the way to the top of the global maximum, and that's it. And it's a very efficient procedure, right? Each one of these searches just keeps track of a single assignment to all the variables in memory. It just updates things, so it's very efficient. You could run many in parallel, and maybe that way you can have a good local optimum rather than a bad local optimum. Okay, as a little quiz to make sure you're 100% clear on the procedure, starting from X, which is over here, where do you end up running this kind of hill climbing search? B, because you climb till you're at this top and you're done. From Y, where do you end up? D, because once you hit D, you don't know where to go. So you end up at D. Maybe if you had some extra thing built in that says if I don't know where to go, I just keep going, just in case that's a clever thing, then you would end up keep going maybe and find E. From Z, where do you end up? E. So what we see here is if we had 3 random starts, one of them would have gotten us to the global optimum, and we can easily verify that, right? If you land here, you know you're doing better than that one over here. All right, let's look at a couple of ideas here to further improve on local search. A lot of them sound even better than they might are, but they have some cool ideas here. Simulated annealing. What's the idea here? We know the issue with local search is that you might get stuck in local optima, right? You're in this local optima and everything's pointing to stay there. So you want to avoid that. So what does simulated annealing do? Well, it still loops and it makes updates. It takes a randomly selected successor, so it picks randomly some next point to move to. So it doesn't say I'm moving uphill, it's saying around me, I pick something at random. Then you check the difference in value for that successor you are considering versus your current point. That difference we call difference in energy. If that difference in energy is bigger than 0, so delta E is bigger than 0, then you make an update, because we're maximizing here, we want to go as high as possible. If it's a step that takes us to a worse spot, Hill climbing would never go to a worse spot. Simulated annealing will consider it. It'll say, well, with some probability I'm going to accept it. And this is how we compute that probability. E to the delta E over capital T. So the worse it is, the lower the probability of acceptance. And in addition, there's the scaling factor capital T. And that T, you think of it as temperature. If temperature is very high, you think of it as there's a lot of energy in your system, you want to randomly move around a lot, your particles are moving a lot, right? Then even something with a very bad energy score is still likely to be accepted. But once your temperature is colder and colder, then once you get close to zero, well, that energy difference gets amplified. It now looks even larger than it already looked because you divide by essentially zero, and the probability is close to zero that you'll accept. And it turns out that if you have the right temperature scheme here, where temperature starts high, so initially you're willing to jump around, but you favor the good things over the bad things, and then you cool down at the right scheme, in the limit, if you're willing to do this infinitely long, you have a very high probability of being in exactly the global optimum of this problem. I'm going to take questions about this after lecture because I want to show one other idea, and I want to make sure we see that. So that's simulated annealing. These are the properties I just mentioned. In practice, of course, running infinitely long is not practical, and so a lot of the cleverness also has to go into what your search operators are. Where are you willing to consider to go as you're doing this local search? Here's the other idea I want to present to you, something called genetic algorithms. What are we doing there? Here we run local search in some sense. We keep around many things at the same time. In this case, we have 4 assignments to our variables that we have in parallel. And rather than just independently running a search, 4 parallel searches independently, we merge what's going on in these 4 searches. How do you merge it? Well, there's something called crossover. And what that means is so actually let's do this first. First thing is selection. So you look at the score of each one of them, and you retain them with some probability based on their score. So in this case, we retained this one twice, we retained this one once, and this one once, but this one disappeared because its score wasn't that great. So that's natural selection is the idea here. Survival of the fittest. The 3 fittest survived, one of them survived even twice. Then there's something called crossover. This is mating, right? As you produce children, your DNA gets crossed over with your partner's DNA, and you get some kind of mixture. That's what's going on here, so you kind of splice your assignment of variables somewhere and combine what you have from the different assignments you're keeping track of. You get some crossover. You again evaluate the fitness. Actually, before you evaluate fitness, you might even do a mutation. That's like the local search step. You do a local update. After that local update, you evaluate the fitness and keep cycling through this. This sounds really cool, of course, and because it sounds so cool, a lot of people try it. It's not applicable to every problem. Really, when this can be expected to work well is if there is some structure in your problem that you can indeed take some subset of your variables. If they're doing well, retain that subset and then merge it with some other subset of variables that are doing well in some other part of your search. But if you don't have that decomposition structure, there's no reason to believe that this step here will do you any good. So it depends on the type of problem whether you might benefit from this or not. N-queens works really well because you can think of as solving one half of the board, another half of the board, you merge the solutions, and often that's a good starting point to then mutate from, which is local search, and then again crossover and so forth. Next time, we'll start looking at search when somebody is working against us or against Pac-Man.